think we should start. Good morning. So today we're going to keep working on this function space f. And I want to discuss this even in odd business a little bit more. And then I want to start introducing calculus into this business. And let me also mention, because just before we started the class, there was another question about this terminology kernel. And I've been thinking about this. Like, why is it the case that we have all these different names for pretty much the same thing? And I think at the end of the day, it's a matter of code switching. You're switching code, okay? It's like you talk one way to your, child, talk one way to your colleague, and so on. And the way you code switch in math or in science is based on what type of problem you're trying to solve, or who are among your colleagues in a certain project, let's say. It's just that. So kernel is sort of like a word that would be that people that are sort of people who are interested in function spaces, for instance, would use, whereas null space is what people who mostly use matrices would use. Okay, so it just changes over time and based on the field. And in reality, you can also think of it that like this. It's like this is just notation. And in a sense, we have sort of like this space of mathematical objects, let's say, and these notations is sort of like bases. You switch bases based on whatever you want to compute. Okay, so that's sort of another idea. In any event, and this is like a philosophical point. Let me just go over this background again. So we have this curly f, which is short for f of r to r, the space of all functions on the real line, defined on the real line, taking real values, single variable real valued functions, and you do vector addition like this, right? So this is vector addition. F plus g equals h means really for any input t, which I interpret as time, f of t plus g of t, these are numbers at this point, when I plug in the time variable, equals h of t. And c times f equals h, here c is a constant, means the same thing as for any time t, c times f of t. This is a number now, so I can number multiply, and that gives me another number. Okay, this is how we add and scalar multiply. We had this specific operator we were looking into. This is a specific case of a graph, affine graph transform. In problem set 6, you're going to see sort of like the general version of this. But this is the one that we're looking into. And this R is acting on f like this. You feed to it a function. It produces another function, R of f. In order to describe what this function is, I need to plug in a value and tell you what this function does to that value. Okay? Functions are defined by what they do. Functions are defined functionally. And so R of f at t is the same thing as f of minus t. So you flip like this. And we came up with two linear subspaces or vector subspaces of f, one of even functions and one of odd functions. And recall that an even function is a function that satisfies this. That is to say, its graph is symmetric along the y-axis. And a function is odd if instead of being symmetric along the y-axis, it is minus the function. If you want, you can think of a function to be odd if its graph is symmetric along the origin. And we also realize that we can also write the space of even functions as a kernel of r minus the identity operator. So you see, now this minus is vector addition or vector subtraction in the space of all linear operators on f. So vector addition in L of f, comma f. Okay. So last week we discussed this abstract formalism, but now that we're done with that, I'm not going to use this alpha and sigma notations. I'm just going to write minus and plus. But this plus is not quite the same plus as that plus over there. This is like a higher order plus, if you want. But at the end of the day, as long as you're aware of the scope of what you're writing down, it should be OK. OK? So now, last week I mentioned that there is a picture like this. OK? So this function space obviously is not quite a plane. It's not two-dimensional. It has many dimensions. And I want to say that this F even, it's also not a one-dimensional space, and this is not a one-dimensional space also. But this is sort of like a caricature, and there is some truth to this picture. So I want to get to this. Now, what I mean by this is the following. I would like to be able to say, before going into that, let me say this. These two function spaces are nice, these two subspaces, but it is not the case that given any function here, it is either even or odd. Right? So if I were to look at the ReLU function, it's a better way of drawing it actually. Okay, so this is a function that is neither even nor odd. It doesn't have any symmetries whatsoever. Okay, I'll call this was the ReLU function. So this is neither even nor odd. So, but instead, I want to say something like this. I want to say, OK, so this particular function is not on this axis, nor is it on this axis, but it's somewhere here. OK? And I would like to be able to do something like this. I would like to be able to take this and somehow project it down to a function here, and project it down to some other function here. So this notation really means that f equals g plus h, g even, h odd. OK? So this is similar to how in the plane, if you have a vector, let me draw it here, similar if you have a vector x comma y, you can project it, well, let me say a and b. You can project it here to the x coordinate, and you can project it to the y coordinate. And so this vector would be a comma 0, and this vector would be 0 comma b. And certainly a comma b, original vector, would be the same thing as a comma 0 plus 0 comma b. Now later on this weekend, we're going to start changing these axes as well, but let's not get to that for now. For now, what I want to do is I want to take a vector, a function, and I want to split it into an even part and the odd part. So here's the example. Let's start with that function, okay, the ReLU function. And let me be explicit as to what its formula is. So this is the box from 1 to -1, 1 to -1. And the graph of the function that I want to split, for instance, looks like this. That is to say, f of t, so this is a vector. Recall that this picture I'm imagining to be one point in this vector space. This function is given by this expression, f of t equals t if t is non-negative and 0 otherwise. So if t is negative. Let me do this. This is the same thing as 2 times this new function, so 2 times f over 2, right? I can scale it by a factor of 2. This is still the box with dimensions, I guess, 2. So instead of going from 0 to this point, I want to cut it halfway there. And look at this function. Okay? Certainly, if I were to take this, scale it along the y by a factor of 2, I would get back this function. So now, let me do this. The same function, drawn twice, of course. Now we have a splitting, but this doesn't quite accomplish anything. I want this function to be even, this function to be odd. Okay? So I need to have some symmetry here, and I need to have some sort of similar symmetry here. What I can do is this. I can try to duplicate the pattern on the right-hand side that I see to the left-hand side. This is going to mess the left-hand side, but perhaps by adjusting this piece over here, I can make them work. So look at this. The dimensions of the box never changes, okay? I'm not writing it down. This is halfway there. This is halfway there. Halfway there. So this stays as is. And now I'm going to put here the reflection of this. Okay. This again stays as is, but in order for this sum to add up to this, which means that on the left-hand side I should add up to 0. Well, the only way that can happen is if I see the same shape on the left-hand side reflected down. Okay. So if you want, this is so this now I can call G. And this I can call H. And note that G is certainly even. It has symmetry like this. And H is certainly odd. And what are the formulas for these? G is, well, I can just write it like this. The absolute value of t divided by 2. And H is just t over 2. Any questions about this so far? So what is the pattern? In order to come up with these two pictures, I used the R operator. And really, I can think of it like this. So let's look at this thing. Yeah, so G of t is the same thing as f of t, my original function, plus its reflection divided by 2. So I started with the function, I added to it its reflection, and I averaged these two functions. You can think of it like this. And h would be f of t minus r of f of t divided by 2. Certainly, if I were to add these two up, I would have f of t plus r of f of t plus f of t minus r of f of t, which means that the r's would cancel, and I have twice f divided by 2 gives me back f. Okay? And indeed, this operation that takes my function and projects it down to g is a certain linear operator whose formula is here. So I can write it like this. So let me define p sub even of f to be f plus r of f divided by 2, and p sub odd of f is the corresponding operator here. Okay. If I wanted, I could also get rid of this f and write these in shorthand like this. So I plus r divided by 2, p sub odd is I minus r divided by 2. I'm going to call this function, this operator, it's a linear operator because it's a certain linear combination of two linear operators, and likewise this. This I call the even projector, and this I call the odd projector. So this is the even projector, and this is the odd projector. Okay? Any questions about this so far?
Is that saying R is just the reflection operator that's associated with any arbitrary linear transformation?
Yes.
And so given any arbitrary linear transformation, you figure out like how to reflect it along the y-axis, and then you feed it to one of those guys, and that is how you project it onto the
You start with any function whatsoever. It doesn't need to be linear.
Okay.
But reflection is a linear operator.
So arbitrary function,
Yes.
figure out how to reflect it.
Yes.
And then that's how you project it and make it fit an even or odd.
Yes.
And that's how you can sort of figure out what components it's comprised of.
Yes.
But then, okay, so I'm sure you're going to talk about Y version.
It helps you analyze. So if you think of these functions as signals, continuous time signals, it helps you analyze. If you take a sort of like a class in differential equations or some other thing, eventually you learn how to split even further this even part using the Fourier series and stuff like that. So they say, for instance, you take this function, you split it into its even and odd parts, and then the even parts split into different cosines, let's say, and the odd part splits further into sine parts. Okay, it's just a way of analyzing things.
Yeah, that's.
Yes.
Is this like plus or minus over here the same like order as the one over there, or like f minus?
What do you mean?
So you said like the vectorization and like those operators are like the higher order ones.
Yes.
Is that the same?
Yes. So this is an average of two vectors, where now the vectors are coming from the vector space of linear operators on F. Okay, so now I went to the higher level. Okay, so F is a vector space, and so is the space of space of linear operators from F to F.
It's like a vector space inside a vector space.
Yes. So think of it like this. This is sort of like Rn, and this is sort of like the space of matrices. You can add and scalar multiply matrices, and matrices are linear transformations. In this case, they're not. There is no matrix whatsoever, but still you can add and scalar multiply. Yeah. So there are further properties, for instance, that is visible from this picture. If I were to start with an even function, there's nothing to project to, right? So that means that if I were to do this, okay, so what does this mean? Just like matrix, so just like taking a power of a matrix, you can take a power of a linear operator. So this is the same thing as applying this even projector 2 times. I'm telling you this is the same thing as applying it once. Okay, let's write it out. So let me first open up this. Based on that expression, this is nothing but p even of f plus r of p even of f divided by 2. Okay, let me now plug in a t value to open things up further. So this is p even of f at t plus, now I know what this is. This is nothing but p even of f evaluated at minus t. So now let's open up these inner p evens using that formula over there. So this is 1 over 2 times, open paren, 1 over 2 times f of t plus r of f of t. This is this, plus, same thing, 1 over 2 f of minus t plus r of f of minus t. Take the 1 over 2's out. That's 1 over 4. So now what do I have? I have f of t plus f of minus t plus f of minus t plus r of f at minus t is the same thing as f of t. Because the point is you put an additional minus in front of the inside of the argument. So you have this. But this is nothing but 1 over 2 times f of t plus f of minus t, which we get, which is the same thing as p even of f at t. So applying the p even operator 2 times is the same thing as applying it once. Okay, if you start with a function, applying the p even operator gives you g. If you apply it again, there is nowhere else to go. It's already even. There is no additional symmetry that you're going to obtain there. And likewise, the same thing holds for p odd. If you were to start with a function f, apply the odd projector to get h, and apply to h the odd projector, you're going to get back h. And for instance, another thing is that if you start with f, apply the even projector to get g, and then apply the odd projector, you're going to get 0. Okay? So the visual effect of applying p even and p odd is simply this. Applying p even means you go down to f even, and applying p odd means you go down to f odd. Okay? Okay? Now, linear operators or matrices, whenever you have a multiplication, if the square of something is the same thing as the thing itself, that's called an idempotent operator or idempotent element. So in problem set 6, there's a similar problem like this. And this time, instead of working on the space of functions, you're working on the space of matrices. And instead of trying to make a function even, in that problem, you're trying to make a matrix symmetric. But the idea is the same. You start with your function. Instead of reflecting along the y-axis, because it doesn't make sense in the context of matrices, what you do is you take the transpose. And the same operators give you the symmetric part of a matrix and the antisymmetric part of a matrix. Okay? And pretty much all of the algebra holds true. Okay? Questions about this? I want to do another example. So let's start with this function. and find its even and odd parts. Now, as you see, if you want, you can argue about, what is happening with vectors in the function space like this, using sort of like an algebraic approach. But I would recommend instead to sort of use a more geometric approach. And so here's how I can come up with the even and odd functions, odd parts of a function. Let's say that my function is this. Okay. Again, I'm going to start with a box of whose sides are, I guess, 2. So this is from 1 to -1, 1 to -1. And let's say that my function is like this. Let me see. So this is halfway there. And then like this. And when I'm drawing it like this, I really mean this just goes on to infinity. But I'm not drawing it. And so this is my function f. And if I wanted to write its formula, I would write it like this. This is equal to 1 over 2 if t is positive, or 0. So 1 over 2 if t is non-negative, and -1 otherwise. Now, if you take this expression, this piecewise expression, and plug it into the formulas over there, it's going to produce for you the even part of the function and the odd part of the function. But let's try to take what these formulas mean and apply them geometrically. Okay? So, for the even part, and I might as well just write it f sub even. Okay? This is supposed to be this, 1 over 2, so the average of f and its reflected version. Okay, so now I can draw the pictures for these. 1 over 2 times, one box for f, and another box for for r of f. Now f looks like this. Okay, this is f. And if I reflect it, I should take this pattern, put it this way. Okay, so this is f, and r of f is going to be like so. Then this is open like this. Okay? Because, this also helps you practice vector addition in this more complicated setting. So now I need to add these two functions. Again, if I wanted, I could just use these formulas. But let's try to do this visually. Okay, I'm going to continue from here. So this is equal to 1 over 2 times. So now I want one box. Okay. So now let's think about this. First of all, at 0, f is at 1 over 2, and r of f2 is at 1 over 2. When I add them up, then now I should get at 1. So here I have this particular point. On this side, this gives me 1 over 2. This gives me -1. When I add them up, I'm going to get -1 over 2. And likewise here, you see? So now I have -1 from here, and here gives me 1 over 2. Add them up, gives you -1 over 2. So this is at height -1 over 2. Scaling this means I just need to squish this picture, and this is what I get. So the box has the same dimensions, but now I get this. So this spatial point is at 1 over 2, and the rest is at minus 1 over 4. It's also a lot more fun, as far as I'm concerned, to calculate things this way instead of that way. Okay? So I started with this signal, if you want, and I did some procedures, and eventually I obtained a certain even function from it. Any questions about this? Okay, let's do the same thing with the odd part. So the odd part of the function should be the same thing as 1 over 2 times f minus this time r of f. Okay. Again, let me draw the pictures. This is f, and then r of f is like so. Now I can go ahead and really take this shape and subtract it from this. But instead, I can also do the following. I can sort of use this to flip this picture to turn this into a plus. And let me do that. So the first picture stays as is. And then now I want to have a plus, and then I want to have another picture over here. So this looks like so. This is f. So now, if I have a plus here, that means that I have incorporated this minus into this picture. Okay? And the way to do this is to flip it like so. Like this, and then like this. So now I need to add these two pictures. And that's going to give me one box. And I can do the same trick before that I used before. This is at 1 over 2 at 0. This is at minus 1 over 2 at 0, which means that when I add them up, I should get 0. Okay? So on the right-hand side, so on this part, this function is at 1 over 2, and this is at 1. When I add them up, that means that I'm going to get 3 over 2. I'm going to go outside the box now. So it's somewhere over here. Okay? And likewise here. This is minus 1. This is minus 1 over 2. Again, I'm going to go outside the box to get this. And finally, again, squishing this picture by a factor of 2, I get this. So this is at 3 over 2, which means that when I squish it, now it's going to be at 3 over 4. Okay. Certainly, this is an odd function, right? So this has symmetry along the origin. And you can also verify that if you take this function, add it to that function, you're going to get back your original function. So I have successfully split this signal into its even component and its odd component. Okay? Yes? Yeah, so what does this mean? So here I'm doing scalar multiplication in the function space. Now what does that mean graphically? I draw the graph of the function, and whatever that number is, I use that to scale the y-axis. That's scalar multiplication in function space. Okay? And likewise, I did the same thing over here, as you see. Any other questions? Okay. So let me say one final thing about this, which is that the even part and the odd part of a function are unique. Okay? Just like in this case, you have a unique x component and a unique y component. Once you split your signal into its even and odd parts, the even part is unique and the odd part is unique. So given f, a vector in my function space, its even and odd parts are unique. What does this mean? This means that if I start with, so if somehow I'm able to split f into g plus h, where g is even and h is odd, then really g has that formula and h has that formula. It cannot be any other functions. Let me write it like this. And this is because of the following. So g plus h, let's say that I have two functions that are anonymous. I want to figure out that g has to be equal to this and h has to be equal to this. G plus h equals f, but f is also equal to f even plus f odd, where these two are given by those formulas. Now, collect the even parts on one side and odd parts on the other side. So g minus f even sent to this side, this sent to this side, gives you minus h plus f odd. Now, these two are even functions, and the space of even functions is a linear subspace, which means that this too is even, and likewise this is odd. So this is an odd function. So whatever this is, okay, let's call it FGH phi. So this phi function is both an even function and an odd function. The only function that is both even and odd is the function that is constantly 0. So phi is both even and odd, which means that phi of minus t is on the one hand phi of t, and on the other hand minus phi of t. The only way this can happen is that phi is the 0 function. That is to say, this has to be 0. In other words, g has to be equal to this, and likewise this has to be 0, which means that h has to be equal to f odd. And this is also clear in the picture. As you see, the intersection of the space of even functions with the space of odd functions is just a point. It is not true, you see, that these subspaces are lines, but it is true that their intersection is a point. Okay, this is where that phi function is. Okay. Any questions about this? Okay. Okay. So now that we're done with this stuff, let's try to incorporate calculus into this a little bit. Before doing that, though, I'm going to introduce a hierarchy of functions. These are pretty much all the functions that you see in a standard and general engineering undergrad education. Hierarchy of functions. So this is going to be a list of vector subspaces of f. The function space f is rather too big in a sense. Certainly you cannot just take any function whatsoever and differentiate it, for instance. So let me introduce these subspaces. And recall that this meant that whatever is on the left-hand side is a subspace, linear subspace of whatever is on the right-hand side. PC, and then R, and then F. So each of these is a function space. Okay? L is linear functions. Linear functions. That is to say, any function here is of the form f of t equals at for some a number. This is a space of affine functions. In the previous problem set, you did look into these two functions. So any function here is like this, at plus b. This is a space of all polynomial functions. So you can imagine that this is a polynomial of degree 1, and generally I can think of a function which is like this. A sub n t to the n plus a sub n minus 1 t to the n minus 1, and so on, all the way up to a sub 0. This is a space of all differentiable functions, so that now we can do a calculus. This is a space of all continuous functions. This is a space of all piecewise continuous functions, like the functions that we were handling over there. Piecewise. Piecewise continuous functions. Let me not write the word functions. And finally, this is the space of all random functions. Or in other words, random variables. Now, if you've heard, so certainly you've heard everything all the way here. Maybe you haven't heard of this. You can think of these as functions whose integrals one can take. And really, when it comes to this, we start being able to use derivatives. Let me just mention, for instance, I'm just going to leave it to you to verify that these are all vector subspaces. For instance, if you have two continuous functions in calculus, they teach you that the sum of two continuous functions is continuous, blah, blah, blah. I rather want to focus on this, and even on this, and some other subspaces in between. Okay. So let me just record that. So certainly D, this curly D space, is the most useful function space here. All the exponential functions and trig functions and polynomials certainly are in it. So derivative operator is linear. So let me denote it by D. From D to D, well, what is D of f at t? This is nothing but, of course, f prime of t, or in other words, df by dt at t. This is yet another function. It's a valid thing to do. And certainly the derivative of the sum of two functions is the same thing as the sum of the derivatives. And certainly if I were to take a scalar and scale it using, so scale this function using the scalar is the same thing as, and then differentiate, it's the same thing as first differentiating and then scaling. That is to say, taking the derivative of a function satisfies the two axioms for something to be a linear operator. Okay? So now here's an example as to where one can use something like this. Consider this, for instance. Let's take three exponential functions with different exponents. Let's say e to the t, e to the 2t, e to the 3t. I claim that these are linearly independent. So f is e to the t, g is e to the 2t, and h is e to the 3t. I claim that they're linearly independent. So I need to take a linear combination of them that adds up to the zero function. So af of t plus b g of t plus c h of t equals 0. Now you see, this applies for any t whatsoever, which means that I can apply derivatives. And I can keep going, right? I can take the second derivative if I want. Now, what are these functions? If I were to differentiate f, I get back f, and this second derivative is also the same thing as f. Right? Because if you differentiate e to the t, you get back e to the t. If you differentiate e to the 2t, you get back 2 times e to the 2t. That is to say, 2 times g. If you differentiate h, you get back 3 times e to the 3t. And so on. If I were to take the second derivatives, now this would be a 4, this would be a 9, and so on. Now let's plug in t equals 0. I can certainly plug in a certain time variable. I'm going to finish this tomorrow because I'm running out of time. If you can finish it, please go ahead and do it. You used something called or computed something called the van der Monde determinant in the previous problem set. I'm going to use it here. Anyway, thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today I want to keep working on this function space business, and I want to go even further, and I want to focus on polynomials. And then we're going to start matching or combining, let's say, this discussion to matrices by way of using bases. So this is the example that we were looking into. I started with 3 functions. So these are vectors in the function space: e to the t, e to the 2t, and e to the 3t. And the claim was that FGH, these 3 vectors in function space, are linearly independent. And recall that yesterday we introduced this new space. It's a vector subspace of the space of all functions, namely the space of differentiable functions. And the reason why I introduced this is because we have this derivative operator, and it's a linear operator. And using this, some calculations become easier to do. And this is one example of that. So what does it mean? So what does this mean? That FGH and function space are linearly independent. So this means that if I were to take a linear combination of them, right, AF plus BG plus CH, and this linear combination turns out to be the same as 0, the 0 vector of the function space, so the 0 function, then it must be the case that A, B, and C, these numbers, are all 0. That is the definition of linear independence. And then opening this box up, because F, G, and H are functions, they are vectors in function space, this equation really means that for any time input t, if you were to plug in the same time into each of these functions, so that now this is a number, this is a number, this is a number, and you're just doing number multiplication here, and then you're adding a bunch of numbers, and this has to add up to 0, no matter what t is. Okay? So this is what we have, and based on this, we would like to be able to say that A is equal to 0, B is equal to 0, and C is equal to 0. So we have 2 tools in our hands. One is plugging in certain t values, specific t values, to reduce this equation over here into a numerical equation. And really that is sufficient, but if you also use derivatives, the calculations become easier. Okay? So for instance, I can do this. Plugging in t equals 0, because I know that e to the 0 is always 1. So let me say this is star. Star gives maybe I should call this star. Well, this is nothing but A plus B plus C, right, equals 0. So I have 3 unknowns, A, B, and C, and in order to be able to solve for them, I need at least 3 equations. Okay? So now I keep going. I can try plugging in some other t value if I wanted at this stage, for instance t equals 1, but then you see the numbers are going to be somewhat messy. So instead of doing that, what I'm going to do is I'm going to differentiate this. When I differentiate, because it's a linear operator, this linear combination relation will hold. Differentiating star gives the following. So now if I differentiate this function on the left-hand side, certainly this is a linear combination, but it's yet another function in function space, I get a f, right, this is f, plus b times 2 times g, plus c times 3 times h. And let me, in fact, do it like this. OK, let me do it step by step. So af of t plus 2bg of t plus 3ch of t equals 0. And then now I can plug in t equals 0 here again to get rid of these functions, because now when I again plug in t equals 0, these are just going to be 1. Gives a plus 2b plus 3c equals 0. This is my second equation. Now I need a third equation. Again, I can differentiate another time. So either I can differentiate this equation over here 2 times, or I can differentiate this first derivative 1 time. Two times twice, and plugging in t equals 0 gives a third equation, which is a plus 4b plus 9c equals 0. Okay. So now we have 3 equations with three unknowns. Okay. So I have one equation coming over there, coming from there, second this one, and third this one. Collecting all of them, the equations for ABC, one obtains. Let me use matrix notation. So my unknowns are A, B, and C. I'm going to put them in a column matrix. And then in the first column, in the first row, I'm going to have 1, 1, 1. In the second one, I'm going to have 1, 2, 3. And the third one, I'm going to have 1, 4, 9. Okay. Just so that this is more evocative, let me write it like this, really. Here I'm going to write 1 squared. This is 2 squared. This is 3 squared. Okay? So now I'm asking, what are the solutions of this equation? Well, note that this matrix has determinant, the same thing as the determinant. So I can take the transpose if I want it. So this is the determinant, and this is a Vandermonde matrix, which you have computed the determinant of in the previous problem set, and this determinant is non-zero. Okay, there's a formula that you computed there. We don't really need the formula. All that really matters here is that the entries are distinct, and whenever the entries are distinct, this is going to be an invertible matrix. And this is invertible means that this, the only solution for this is ABC 0. Hence, we have what we wanted. We were able to verify that A, B, and C have to be 0, which means that indeed F, G, and H are linearly independent. Okay? Now, of course, there's nothing special about the exponents that I used over there. If I were to take 3 exponential functions with distinct exponents, they would be linearly independent. And I also don't need to take 3 exponential functions. I can take any number of finitely many exponential functions, and the same argument would work. Right? There's always, for any n, there's a van der Monte matrix like this, and you can compute the determinant, and it just says that as long as the entries are distinct, the determinant of the van der Monte matrix is going to be non-zero. So it will be invertible. So more generally, let me write it like this. If R1, R2, dot, 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 Rp, any number of numbers are distinct numbers, then the functions e to the R1t, e to the R2t, e to the Rpt in function space are linearly independent. Okay? Now, what does this mean? If I were to take p exponential functions whose exponents are distinct, I'm telling you that these are linearly independent by the same argument, essentially. If this is the case, their span inside this function space is p-dimensional, and consequently these constitute the basis for that span. But if that is the case, then F contains a vector subspace of p dimensions for any p. So thus F contains a linear subspace of dimension p for any integer p, for any positive integer p. If this is the case, then the dimension of this function space, which is a vector space, must be larger than any integer. So that is to say, its dimension has to be infinite. Because imagine this. I can take as many exponential functions as I want, and based on this argument, what I'm telling you is that each exponential function that you're choosing, insofar as the exponent is distinct, is a new axis in your function space. So you have infinitely many axes, okay? And this is not even everything, okay? Even beyond these exponential functions, there are so many other functions in this function space. So this is a huge vector space. Let me also add this. This is sort of like an exercise. I think that this is nice. You can apply a similar argument to functions of this form. Instead of just looking at exponentials, you can also add a little bit of a polynomial piece and a trig piece. So for instance, if, let me say it like this. Mi, omega I, and Ri are distinct, then t to the mi times cosine of omega it times e to the rit are linearly independent. Okay? This is a nice exercise. You can take any finitely many distinct triples and look at functions of this form. So it's a product of a polynomial and a trig function and an exponential function. And then go through the argument, use derivatives and so on. And you would be able to show that they are indeed linearly independent insofar as the numbers that you chose are distinct. So here's an example for that. Let me just take a simpler case. Certainly we did 1 against t. Okay, so I didn't consider these two pieces. I said I'm looking at t to the 0 and t to the 1, and they turn out to be linearly independent. I can look at this, for instance. Let's just look at cosine and sine, for instance. I can do that too. This is cosine of t, g of t. Let's do something slightly more complicated. Is sine of t, h of t is cosine of 2t. Now, there are double angle formulas and stuff like that which write this in terms of these two, but that expression is not linear. Okay, so you have to multiply this by itself, which means that it's not a linear relationship. So the claim is that, again, these three functions are linearly independent. So claim you're going to see problems like this in problem set 6, where you have already seen them if you looked at it. That's why I'm going over. So I'm going to do the same thing. Okay, I'm setting up a general linear combination, and I'm saying that, okay, so let's say that it is 0. Can we figure out that the constants that I'm using are really 0? So setting up the equation, I have this. Okay, and given this, I want to say that A, B, and C are 0. So first of all, I have cosines and sines. If I were to plug in t equals 0, right, so sine would vanish, and I would get cosine of 0 is 1, cosine of 2 times 0 is also 1, so A plus C is 0. You see, by either plugging in certain values or by differentiating and then plugging in certain values, I'm trying to extract certain linear algebra stuff, like numerical equations that I know how to deal with. These are sort of more complicated vectors, but I'm sort of trying to reduce the problem into problems that I can solve. And then I can, for instance, plug in pi over 2. Would this work? Okay, so if I plug in pi over 2, this becomes now 0, right? Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi is minus 1. Right, so it's this way. So I should have 0 here. This is 1, so this is B, and then minus C equals 0. Okay? Let's do one more thing. So I need one more equation because I have 3 variables, 3 unknowns. Yeah, why not? Let's just differentiate and then plug in a certain value. If I were to differentiate this equation, so let me just say this. Differentiating gives, so now this is a minus sign, minus a sine of t. This becomes b cosine of t. And then this becomes c times, or minus 2 times c times sine of 2t. Minus 2 c sine of 2t. And of course, the right-hand side has to stay 0. Okay? Okay, so this is very nice, you see, because now if I plug in t equals 0, this is going to be 0, this also is going to be 0, and this is going to be 1. So I would have just b equals 1, b equals 0. So this is 0, this is 0, this is 1. So b has to be 0. If b is 0, then so is c. If c is 0, then so is a. So there are multiple ways of verifying this, of course. I just decided to choose these specific steps, evaluating at this particular time, that particular time. Of course, in this case, since I know that cosine and sine have these like specific values that they work well with, I'm using those things. And of course, another thing that I use is the derivative, which is a useful thing because cosine, when differentiated, becomes a multiple of sine and vice versa. Okay? Questions? Yes?
So I see how you can like do it with like the derivative, like that makes sense, but could you, so the integral would also be a linear transformation, right?
Yes.
But you couldn't say that, well, you could say that like the general form of the integral is linearly independent if the function itself is linear, but you couldn't like say a specific, like you couldn't integrate like let's say twice, and because you have a plus c, and that could go to an x.
Well, there are multiple ways of integrating things. One is the antiderivative,
Yeah.
and the other one is the integral whose variable is one of the bounds of the integral.
Oh, yeah.
So if you want to do the analogous thing with integrals, you want to have an integral whose bound is the variable now.
Yeah, so you could just value.
Yes. Yeah. Any other questions? Okay, so now let's do the same thing with the polynomial pieces. I want to focus really on these polynomials. And really, well, okay, so let's do this. Recall that last time I defined this even smaller subspace than the differentiable functions, namely the polynomial functions. Certainly polynomial functions are differentiable. And let's just stick to polynomials. My claim is this. And let me, going forward, let me stop writing this f, g, h, and so on. Now that we understand these are vectors in a vector space, I don't want to use like a separate name for the function. Of course, if you want, and if you're getting confused, you can always do this. But just for brevity, let's say, let's look at this. 1 t squared, t cubed, dot, 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 t to the n. I'm taking what are called the monomials. And so these are all vectors in curly p. In the book, they use this blackboard bold p. It's the same thing. I'm not using this notation. Okay, this is often used for something else, like probability or something. It's better to use something like this, and it is more sort of compatible with the notation that we've been using so far. The claim is that these are linearly independent. Again, I'm going to set up the equation. So let's write it like this. A0 times 1 plus A1 times t plus A2 times t squared plus dot, dot, dot plus an times t to the n. Right? I took an arbitrary linear combination of these vectors in function space, in the polynomial space. And I need to set this equal to 0. So you see, what you can do is this. Plug in t equals 0, everything except the constant term is going to vanish, right? So if I plug in t equals 0, all of these guys are going to vanish, and I'm going to have a0 equals 0. Okay? So I can differentiate if I want, or I can do something else. Let me not differentiate. If you wanted, you could use differentiation, of course. If this is the case, I can do this, okay? So this expression, so the left-hand side, really is starting from a1 times t all the way to here. which means that all of these terms have a factor of t. So I can factor that out. T times a1 plus a2t plus dot 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 plus an t to the n minus 1 equals 0. Now observe that the point is that this expression, this equality should hold for any t whatsoever. Plugging in t equals 1 tells me that, so this is a product. Either this is 0 or this is 0. Plugging in t equals 1 tells me that the sum of these guys have to be 0. Maybe that's going to get more complicated. I'm backtracking. Sorry. I'm going to differentiate after all. So I have that a0. You could actually complete this argument, but it's going to take longer. Let's go back to this step. So I have that this is 0. So now I can differentiate. Differentiating this term, the remainder gives me this a1 plus 2 times a2t plus 3 times a3t, and so on. So right, so because when you differentiate one of these guys, what you do is you take the exponent, whatever the exponent is, you subtract 1 from it, and you put this exponent as a scalar in front. So that's what I did, for instance. T squared, when differentiated, becomes 2t. And then again, I can apply the same reasoning I did before. I can plug in t equals 0. Now all of these terms would vanish, and I would get that a1 has to be 0. And I can keep going like this. As you can imagine, I can keep differentiating and get rid of these pieces, differentiate this to turn this into a constant, and so on. So okay. So that means that these terms are linearly independent. For any t, for any n value. So if I go all the way up to 2, okay, so that gives me 3 vectors. They are linearly independent. If I go all the way up to 15, now that gives me 15 linearly independent vectors, and so on. And they're all inside this space. And by the same argument over there, I have that this space of polynomials is infinite dimensional. Okay? So whenever you have infinite dimensional things, even though perhaps you could apply matrices in certain situations, certainly you would need to use infinite matrices. But if you want to use the machinery that we've really developed so far, that is to say finite matrices, we need to look at finite dimensional subspaces of these things. And so what you can do is you can concatenate the dimension. So instead of saying I'm going to look at all polynomials, you can say I'm going to look at polynomials of degree at most 3, for instance. So let me introduce another notation. P sub n, in the book they write it like this, blackboard bold P sub n, is the, so let me write it like this. This is a vector subspace of P, is the linear subspace of polynomials, polynomial functions, let me say, of degree at most n. Okay? And so for instance, if I were to plug in n equals 1, P sub 1 would be the space of all polynomial functions of degree at most 1. Right? So the degree there is the exponent that you see. So this is the degree 2 term, this is the degree 3 term, and so on. This is the degree n term. And if I'm looking at P1, that is to say, so if I'm looking at P1, the largest power I should see is 1. Okay? So this is the same thing as A plus BT. Maybe I should say AT plus B. Okay? In other words, this is nothing but the space of affine functions from R to R. From R to R. Which I think we denoted by curly A. Space of affine functions. Space of real valued single variable affine functions. Single variable real valued functions, affine functions. Okay. Now, what is the basis for this space? Any ideas? So this is a certain vector subspace of the space of all functions. It's certainly a lot more restricted than the whole space, right? So because the graph of any such function is a line. Possibly through, it may not pass through the origin, but it may. Okay. So I can't just take any function whatsoever. Any ideas as to what the basis for this is?
I just want to make sure, because we're treating like the functions themselves as vectors.
Yes.
You can't take like the unit vectors 1, 0, and 0, 1 as basis elements because they themselves are not functions.
I mean, what is 1, 0 in this context? You need to give me a vector. And a vector here is a function.
Could you do like AX and AY or something? Like something sort of analogous to like...
I want a function of time.
Does it being a function of only one variable mean that it's one-dimensional?
Not quite, because we were already looking at this function space f. Each function in this function space is single variable, but it is infinite dimensional. Look, any vector in P1 is a linear combination of 1, which is the function that is constant, and t, which is the diagonal function. And based on this example, we have that they are linearly independent. Okay? So, any function in P1 is in the span of 1 and t, the vectors 1 and t. Okay? So by definition, of P1, any, let's say, P in P1, right, is in the span of the function 1 and t, the function t. Okay, that's literally what I'm writing here. Right? It says a times t plus b times 1. And based on this, and based on actually what we discussed a while ago, I think, these two functions are linearly independent. Okay, so you have a set of vectors that are both linearly independent and span the space. Okay, so that's the definition of a basis. Let me write it like this. Is a basis for P1.
So if you have p to the n, the basis is 1 through t to the n.
Exactly. Consequently, the dimension of P1 is 2. The dimension of Pn is
Pn, or n.
plus 1. Yeah, this is like confusing. I understand. Yeah. So the subscript is not the dimension, but the degree. So, yeah. So the dimension of P1, you see it's a function space. And we have examples of function spaces that have infinite dimension, but this happens to have finite dimension. So it's a plane. It's a plane. It's a literal plane inside this infinite dimensional space of functions. And generally, of course, this equals n plus 1. Okay? So if I want, I can do this.
So the dimensions are infinite if you can take infinite derivatives of the functions.
It's not about being able to take the infinite derivatives. It's about being able to come up with infinitely many linearly independent directions.
And that's just and that's also, but that is also correlated with derivatives.
Yeah. So here's a picture then. I have my function space. I'm going to try to draw it. Okay. So we know that it has an origin. It's a vector space. It has an origin. The origin is a function that is constantly 0. What we write here, this. This is the function that is constantly 0. So it's at the origin. Now I have, for instance, here, somewhere here, e to the t. Somewhere here, e to the 2t. Somewhere here, e to the 3t. Here it is e to the 4t. Of course, I'm drawing this in the plane, but you're supposed to imagine that the so to speak, angle between this and this is 90 degrees. This and this is 90 degrees. This and this is 90 degrees. This and this is 90 degrees, and so on. So each one of these is a separate dimension. So already we're at 4 dimensions. Okay? So I have one new direction for each e to the rt. Separate from these, somewhere else I have cosine. I have somewhere here sine. Here it says cosine 2t, linearly independent from everything else. Their products is going to be linearly independent again, so that's yet another direction. So you see I have infinitely many directions. But somewhere here I have the constant function, and any other function that is constant is along this line. And somewhere here is the function t, and any other function that is a scalar multiple of t is on this line. So now we just look at this 2-dimensional slice. This is a literal 2D slice inside the function space. Okay? And now let's try to tie this back to a comment that one of your colleagues made, which is that it should be something like 1, 0 and 0, 1 then, if it's a plane. Okay? So forget about all these functions and everything. If it's a plane, I should be able to treat things as x coordinates and y coordinates. And that's where the basis comes in. Okay? And for this, we need this notion of an isomorphism and invertibility in the abstract setting. So let V and W be vector spaces over the same field, which is R for us. So the scalars are coming from R. I'm not going to write this alpha and sigma and everything. So it's just plus and scalar multiplication, but they might mean different things. A linear transformation or a linear map from V to W. So T, a linear transformation from V to W, is called invertible. You see, in this case, I cannot really talk about row reduction or anything, or I cannot talk about determinants even, but I can talk about invertibility. If there is an S going the other way around, so from W to V, such that first applying T and then S gives you the identity transformation of V. So S T V equals V for any V in V, and T S W equals W for any W in W. In this case, it turns out that this inverse, if the inverse exists like this, it is unique, just like with matrices. And of course, people write it like this instead of writing it S. They just write it like so, t to the minus 1. And in this case, if you have two vector spaces such that there's an isomorphism between the two, there's an invertible linear transformation between the two, you call them isomorphic as vector spaces. So that's a fancy word.
If there was what relation between them, then it's isomorphic?
So you take two vector spaces, and you're looking at possible linear transformations between them. If you can find a linear transformation that is invertible, you call the vector spaces isomorphic. If there is an invertible T linear transformation from V to W, then V and W are said to be isomorphic. As vector spaces. Maybe they're not isomorphic as something else, but as vector spaces, they are isomorphic. There's a linear transformation that transforms one vector space to the other one, and you can go back. Isomorphism, or isomorphic, means morph is the shape and iso is the same. Same shape, same kind. And in this case, this invertible transformation is also called an isomorphism between them. In this case, T is called is said to be an isomorphism. Linear isomorphism, if you want to be more precise, from V to W. People also write this, right? So instead of writing equal, they put a twiddle on top. This is like a notation for it. Okay. So whenever I was really saying previously, let's interpret this as that, I was really using this rather formal idea of an isomorphism between vector spaces. And in particular, in this case, what I'm really saying is that the space of polynomials of degree at most 1, that is to say, the space of affine functions, is isomorphic to the plane, to R2. And in fact, instead of going to the plane, let me go to the space of matrices. So P1 is isomorphic to the vector space of 2 by 1 matrices. Okay? So I need to display a linear transformation from this to this that is invertible. So here's a linear transformation. So what's the idea? I need to start with an affine function, at plus b, and I need to store it in a 2 by 1 matrix, that is to say, in a column matrix. So let me write it like this. If P is at plus b, it's a certain vector. What is T of P? How can I store this function in a matrix?
First one would be AT, the second one would be B.
Well, yes, but then my entries, I want to be not functions, but numbers. So I want to forget that T, forget about that T. I want to forget everything about this being a function.
I guess you could, like, if you just stored it in a 2 by 2, you have like A, B, 0, 1. And
2 by 1.
Oh.
So I have two spots, two numbers.
You just put A and B in there.
Okay? Now the claim is that this is an invertible transformation. Okay? So what is the inverse of this? Well, the inverse of it is that if you take a column vector, AB, interpret it to be this. That's the inverse. Okay? So now, underneath this really is this basis that we really chose. The way you decided these two, and it is, of course, something that works, is related to the basis that you were using. In this case, the basis that we have, did I erase it? Oh. In any event, so T and 1 is a basis for this space, we said. So A, the coefficient that you put at the top into that matrix, came from this T element, and B, the second entry in the matrix, came from the other element in the basis. So here what you really did is, in the first entry of your matrix, put the coefficient of t, and you said in the second entry, put the coefficient of the constant function. What I'm trying to say is that this particular isomorphism that we wrote is purely dependent on the basis that we were looking into. Okay? T is determined by a choice of basis for P1. Okay? So tomorrow and on Friday, we're going to keep looking into this basis matters even further. You see, it allows you to compress information quite a bit, and it allows you to start using matrix algebra even when the original context is much more abstract. Like, let's say the function space or something like that. Insofar as you have finite dimensions, everything that we applied becomes applicable. We learned so far becomes applicable to the situation. Insofar as you know how to store things in matrices. Okay? That's it. Thank you. I'll see you tomorrow. Okay. Good morning. So today we're going to do some abstract work, I think. And we're going to put ourselves in some straitjacket. Just so that we understand what we're trying to do here. So the whole point is understanding bases as coordinates. And in a sense that a lot of the computations that we were doing so far are dependent on what type of a basis you're using. And consequently, if you were to change your basis, if you were to change how you look at the world, let's say, computations would need to be changed also. So interpretations, you see we had a lot of these like higher level interpretations. I can think of this matrix as this transformation and so on. So these are going to be under construction, but still we have these things, okay? We still have matrix algebra. If you're given matrices, you know how to multiply them, add them, scalar multiply them, whatever. You also still have switching between systems of linear equations and matrices. You have Rn. You have all the vector spaces, of course. You have Rn, but a vector in Rn is only an n tuple. So it's like you just list a bunch of numbers. That's all you have. And you can add them and scalar multiply them. You have arbitrary vector spaces, subspaces, linear transformations, invertibility, and so on. So all of the abstract machinery you also have. What you don't have is that vectors in Rn are the same thing as column matrices. We don't have that. And we don't have that linear transformations. So this linear transformations from Rn to Rm is the same thing as m by n matrices. We also don't have that. Okay? So somehow you see the left-hand sides are sort of more abstract, more geometric if you want. Right-hand sides are more computational. Because what we're going to realize here is that instead of perhaps writing that these are equal, a more accurate way of writing these is to say that Rn is isomorphic to this, and this vector space is isomorphic to this vector space. So more accurately, for instance. Okay, so we're going to put this twiddle on top of the equal. Recall that this was the shorthand for isomorphic. Isomorphic as linear spaces, as vector spaces. Okay, so and maybe I should mention this actually. Well, I'll mention it later. The one perhaps thing that would be nice to mention here is sort of this distinction between the type and the token. Okay? So this vector space is the vector space of n tuples. Okay? Whereas this vector space is the vector space of n by 1 matrices. Clearly, they're distinct things, and I have different notations for them. So, but even though that is the case, the way you do vector addition and scalar multiplication in this vector space, and the way you do vector addition and scalar multiplication in this vector space, are so that these two spaces are indistinguishable as vector spaces. Okay? So that is to say, these two have the same type, but they are distinct tokens. Okay? Now, this is like a big distinction in philosophy, and I tried understanding this earlier this week. It's somewhat confusing, so if this is confusing, just like skip it. But so this means V and W have the same type, but they are different tokens. Okay. A philosopher might disagree with this statement, but we're not doing philosophy here, so we're all good. Okay. So, I mean exactly this. It's like they look different, but they act the same.
Could you swap tokens with symbols? Or does token imply some sort of functionality that doesn't exist in our context but somewhere else?
So okay, think of it like this. I'm saying that these two are the same vector spaces. Okay, so let me go even further, okay? So here's an example. Rn, according to this, is isomorphic, okay, to this. But then using the second row, this is also isomorphic to the space of linear transformations, right, from Rn to R. Okay? So clearly this is a distinct thing from this. But as vector spaces, their structures are the same, but they look different. They look different, they act different at first glance. But underneath, there's an isomorphism that relates how things are, how we can do vector addition here, and how we can do vector addition here.
So the tokens in this case, say you had a matrix or a vector of numbers, the tokens in that case would be the numbers. The numbers look different, but because they can kind of change different.
Yes, I think so. So I think, so maybe, let me say this example. So for instance, if you take a sentence in English, you translate it into German, it's the same type, different tokens. Okay? Yeah, well, I should not get into philosophy. It's messy. Anyway, so what I want to do is this. I want to really think about how originally we were switching between Rn to the and these matrices. Okay, so and really this had to do with this standard basis is the name that we were using. So let me write something here. So here's some stuff about bases. So first of all, this is one observation. And I'm going to do this rather abstractly so that we don't get confused about the things that we're comfortable with. So let V be a vector space. So this is this abstract, mysterious thing. Our idea, or what we're trying to do here, is to reduce everything, vector addition, scalar multiplication, linear transformations, and everything into matrices. Okay, but these are some weird stuff. I have some addition, some scalar multiplication. And say beta is a basis. For V. So what does this mean? This means that I have beta 1, beta 2, all the way up to beta n. These are all vectors in V, whatever that means. And they are linearly independent. And they span. So, i.e., or more explicitly, we have that all these are vectors in V. Okay, first of all. So it's an ordered tuple of vectors. Span of them is V. That is to say, any vector in V is a linear combination of these. So okay. So you see, this is promising because at this stage, I don't know what vectors in V are. I don't know what these guys are. All I know is that they constitute a basis. And in this stage, at this stage, a linear combination, no matter how abstract the vector space is always using numbers. Okay, so this is giving me numbers. So V equals C1 beta 1 plus C2 beta 2 plus dot 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 plus Cn beta n for some number C1 to Cn. So numbers are concrete things. But of course, observe that certainly these numbers should depend on the vector, but also they should depend on the basis elements. Okay? So this is the important thing. These numbers, they are concrete, but they depend on the vector, of course, and also the basis. Okay. Which depend on V and beta. Okay? So that is to say, if I were to take a different basis for the same vector space, the same vector would have, again, an expansion like this. You would be able to write V using some other basis, but the numbers would be different. Okay? And the third property, of course, is that these are linearly independent. Okay? So what does this mean? It means that if you were to take the zero vector of your vector space, since it's a vector, it has so it can be written as a linear combination of beta 1 to beta n. But in this case, what I'm saying is that it must be the case that C1 to Cn are all 0. Right? That's what it means for these vectors to be linearly independent. So let me say A1, B1, beta 1, A2, beta 2, dot, 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 AN, beta n means A1, A2 equals AN equals 0. Now this 0 is an abstract 0. Okay, it's defined as something, so it's defined as this 0 vector. Okay, this is a 0 vector, it's abstract. This is concrete, this is a 0 number. Okay, so now the first thing is this. Not only is it the case that any vector can be written as a linear combination, so that if I fix the v, C1 to Cn are going to be unique. So not only they exist, but they are going to be unique. So above, given the basis beta, so let me say for fixed basis beta, and a fixed vector, C1 to Cn are unique. Why is that? Well, note this. Okay? So this is what we have. And let's say that we have some other numbers, d1 to dn, that if we use them as weights in this linear combination, we again get v. Well, send everything to the other side and collapse things. So C1 minus D1 times beta 1 dot 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 plus Cn minus Dn beta n equals 0. But then it is part of the definition of a tuple to be a basis that they are linearly independent, which means that this is a 0 vector, which means that all of these coefficients have to be 0. Let me just write Ci equals Di. Okay? So you see, not only do we have a concrete representation, these n many numbers for a vector, but that representation is unique if you fix the basis. If you fix the basis. Okay? So here, let me give an example to this. Let's consider R2. Now, I'm not going to think of the vectors in here as 2 by 1 vectors. They're just going to be pairs of numbers. So let me consider, for instance, this basis. So 1, 0, and 0, 1. So this is a standard basis. This is the name for it. So this is a standard basis. Let me take some other basis, and let me call it gamma. For instance, I can take 1, 0 and 1, 1. Let me take another basis, delta. I'm just going to take beta, but I'm going to switch the orders. Yeah. I'm not going to do it, actually. I decided not to do it. Let's just keep these two. OK? So now, if I were to take a v in R2, by definition, it must be of the form x comma y for some numbers x and y. Now, maybe I should write a and b, a and b. Okay. So if I were to use the first basis, I want to split it. I want to split this vector using the basis elements for this basis. So I would write it like so. So I want to have some constant multiple of 1, 0 plus some other constant multiple of 0, 1. Of course, this has to be a, and this has to be b. There are no other numbers that, when put into this linear combination, gives me this vector. Okay? It's unique representations. But if I were to switch my basis, now, instead of using these two vectors, I'm trying to use these two vectors. OK. So in this case, what I can say is the following. Again, I want to come up with numbers. Whatever I put here is not going to be able to affect this coordinate, which means that, and it's coming from here, which means that this coordinate has to be b. OK, this one is the same. But if this is b, I'm already adding to the first coordinate b, which means that in order to get a at the end, I should put here a minus b. OK? So depending on which basis you're choosing, the concrete expression of the vector that you chose, of the vector that you're looking into, is going to be different. OK? So this is the first idea. The second idea is this. If you have a basis for your vector space, let's say beta 1 to beta n, any other basis, 2 is going to have n many vectors. So instead, let me write it like this. So let V be a vector space and beta be a basis then if gamma, let me say, now gamma is using somehow m many vectors, 2 is a basis, then it must be the case that really m and n are the same numbers. Okay? So that is to say, if you were to fix a vector space, it is likely that it's going to have many different bases. But what's going to not change is the number of vectors in this, in whatever basis you're looking into. It's always going to have the same number. And really, once you have this number that is constant, regardless of the basis you're using, is called the dimension of the vector space. So this constant let me write it like this. The dimension of V is defined to be this constant integer. Okay? I don't think proving this is very illustrative, so I'm just going to leave it like this. Certainly it is believable. In the above case, you can imagine how in R2, you certainly need exactly two vectors. Now, this is not saying that if you have two vectors, they're going to be a basis. But there, it is saying that if you're not taking two vectors in this, it's not going to be a basis. Okay? So, any basis of R2 must have exactly two vectors. Okay, let me write this explicitly. If you have two vectors, two arbitrary vectors in R2, I'm not saying that they're going to constitute a basis. All pairs of vectors constitute a basis for R2. Okay? You've done exercises that were sort of leading up to this. You were given, let's say, 5 three-dimensional vectors, and the question was, are they linearly independent? Cannot be, right? Or you're given 2 vectors in a 7-dimensional space, and they're asking, does it span everything? Certainly cannot. So, sorry, we weren't using these. So this is a basis. But if I were to take just one vector, right, not a basis. In R2. If I were to take 3 vectors, not a basis. Okay? Any questions about these so far?
So far we haven't talked about the orthogonality.
No. No.
What does it mean? Like, I understand, like orthogonality.
Orthogonality. We're going to talk about it later.
Okay.
Yeah.
Later then.
Yeah. I mean, as a working definition, you can take it as, so you can say it like this. The 2 vectors are orthogonal if their dot product is 0.
And in R2, that means perpendicular.
With respect to the, so what do you mean by perpendicular?
Well, I guess like if we were working in the context of constructing a house,
Yes, yes, that is true.
we would mean it.
Yes,
Perpendicular.
yes, yes, yes.
What's up?
Would it be the tangent to or the perpendicular line?
What do you mean by tangent to the perpendicular line?
If you had 2 points, the dot product would be the one facing exactly away from it, and then 90.
Dot product is going to give you a number. It's not going to give you a vector.
Oh, cross product.
Yeah. So it really is giving you the angle between.
Oh, okay.
Yeah.
So even beyond R3 in n dimensions,
Yes.
the concept of a dot product equals 0 involves so-called
Yes. Yes.
Can I ask one?
Yes.
So what we've done so far is like just make the definition of, like that's pretty much the definition of linear independence to me,
Mm-hmm.
but as generic as possible.
Mm-hmm.
And so I guess if you want to like leverage all of these definitions in whatever context you're working in, you just have to ensure that for whatever vectors you're talking about, addition and scalar multiplication are defined in some sort of meaningful way.
Uh-huh.
And then you can just do all this stuff.
Yes, but so for instance, one of the problems in problem set 6 is asking you to verify the following. If you have an arbitrary vector space, maybe infinite dimensional, maybe not, they don't give you. But they just say this. If these two, so you have two vectors, if they are, they constitute the basis, so that now it is two-dimensional, I guess, then so does x plus y and x minus y. This is purely abstract. Maybe I should keep going so that perhaps. No, I understand. Like it's hard to perhaps. Maybe I'm having trouble justifying why we're doing all this, but. Let me just keep going, and then if the question persists, then we can perhaps think about it even further. So now that we have these two properties about bases, okay, so using a basis, I can take any finite dimensional vector space. And so what is a finite dimensional vector space? A vector space is finite dimensional if it has a finite basis, okay, because its dimension is the number of vectors in the basis. So the space of polynomials is not a finite dimensional space because we have arbitrarily many linearly independent vectors in it. Yeah, sorry, I guess what I was trying to say was that you can have linear independence without spanning things. So you want a representation, and you want a unique representation. So I guess that's what I was trying to say. And this is the context of what I'm going to write now. And so this is bases as linear coordinates. Okay? So the main idea is this. Whatever vector space we have, no matter how abstract it is, insofar as it is finite dimensional, that is to say it has a finite basis, we would like to reduce it we would like to reduce linear algebra in that vector space, in that mysterious vector space, to just matrix algebra. So let B be a finite dimensional vector space. And let beta be a basis. So here I'm saying n is the dimension of V. Now define this isomorphism, this linear map. M sub beta, this is going to be an isomorphism of vector spaces going from V, okay, to the space of matrices of dimension n by 1. Now, so this is going to be a linear transformation, which I hope is going to be invertible, is the idea. Recall that that's what it meant for two vector spaces to be isomorphic. So if I take a vector here, I know that, so it is of this form for unique numbers, C1 to Cn. Okay, so because of this, perhaps, so if you want, you can think of it like this. C1 is really C1 of v comma beta, right? They are like functions of the vector and the basis. So Ci really is a function of v and beta. Now, this linear map does this. Okay. I'm not thinking of M sub beta as a matrix itself, although I could if I wanted. We're going to get to that later. This is just a vector. This is just a linear transformation because it abides by this axiomatic definition of a linear transformation. Okay? So I think I'm going to leave it to you as an exercise. This is a good exercise. And exercise. Verify that M sub beta is an invertible linear transformation. This is a very good exercise. So you need to verify that M sub beta is a linear transformation. That is to say, if you were to take two vectors, add them according to the vector space addition in V, and turn it into a matrix, that matrix will be the sum of the corresponding separate matrices. And you really need to use these linear combinations in a very controlled manner. Okay. But let's just take that for granted. It's an isomorphism, in other words. We call that a linear, invertible linear transformation was called also an isomorphism. So V, this mysterious vector space, might look very different from this space of column matrices, but insofar as linear algebra is concerned, their structure is the same. It's a translation, okay? It's a foreign language, okay? So this is like I don't know, some language that you don't know, but there's a translator and translates it to a language that you understand. You know how to do matrix algebra. You can handle matrices. You don't know how to handle this, okay? So here's the example. Let me just look at a couple of bases. Again, my vector space is going to be R2. Okay, let's look at these three bases. So the standard basis, this other basis, and this other basis. Okay, so now note that in beta and gamma, in beta and delta, I'm using the same vectors, but they are flipped. Their orders are switched. Okay, now these are distinct bases because the vectors are supposed to be ordered. So let's take, for instance, as V, let's take the vector 2, 5. Okay, so just like I did over there, I need to split this vector using whatever basis I chose. And that's going to give me numbers. I have numbers already, but this is faulty, okay? So in a sense, don't trust the numbers that you're seeing here. So using the first one, I have this. So some number times the first vector plus some other number times the second vector. And of course, this has to be 2, this has to be 5. Now, based on this splitting, then I can say that the matrix representation of this vector with respect to this basis is 2, 5. So let me write it like this. Okay? And certainly this is what we were doing before. Because this, I said, recall, I called this the standard basis, and we were really using this specific isomorphism between R2 and the space of column vectors. You said, oh, you know, like first entry goes to the first row, second entry goes to the second row. But this is not, in a sense, natural or canonical. So if I were to use the second basis, so now the first entry is, so the first vector is 1, 0, and then the second vector is 1, 1. Now, we did that over here, but let's, again, try to compute this. Again, the idea is that I cannot contribute to this 5 using this vector because its second entry is 0. So this is not going to affect anything. So that means that I need to use some of this. But if I'm going to get 5, that means that this has to be a 5. If this is a 5, in the first component, I have 5. But I need to have 2, which means that this has to be minus 3. Okay? Which means that the basis, the matrix representation of the same vector, okay? This vector is the same vector as this vector. But as matrices, they look different. Okay? Any questions about this? Okay? Now, if I were to do the same thing with the third vector, so now you see, in the first spot, I should have this vector. So instead of having this in this order, I'm going to have the other way, the order in the other way. So now instead of having here a 2, I'm going to have a 5. And then 2 is going to go here. So the matrix representation of the same vector again, with respect to this third basis, is 5, 2. Okay? So as you can see, this can get confusing. Let me also say, in the book, they're using a different notation. Instead of writing it like this, I think they write it like this. So 2, 5, bracket, sub beta. Okay? But I'm explicitly using this notation. It's the matrix of, right? So this is an operator that takes a vector as input and gives you a matrix with respect to the basis that you chose. Okay? I think this is better notation, so I'm just going to stick to this. But if you want, you can use this notation also, of course. Any questions about this? So what we're going to be interested in is to switch between different perspectives. So think of bases as different perspectives. So with respect to one perspective, 2, 5 is this matrix. With respect to another perspective, 2, 5 is this other matrix. Okay? And of course, the same complication holds in the context of linear transformations. Okay? Any questions about this? I was expecting more questions, I think. Okay. Now, if that is the case, then I should also be able to turn any space of linear transformations between two vector spaces into a space of matrices. Oh, before going into that, perhaps I should do some other thing. Another example. Here's another example in P2, for instance. Recall that P2 was the vector space of all polynomials or polynomial functions of degree at most 2. I guess yesterday we did 1. Let's do 2 today. And so any vector here looks like this, right? So a0 plus a1t plus a2 t squared. a0, a1, a2, real numbers. So the standard basis here is the constant function, this monomial, and then t squared. Okay, it's a basis. And with respect to this basis, the polynomial, for instance, 2 minus 5t plus 2t squared becomes 2 minus 5, 2. Right, because I have 2 of the first guy, which means that I'm putting it into the first row. I have minus 5 times the second guy, so minus 5 goes here, and 2 times the third guy. But here's another basis. This is also a basis. So to compute the matrix representation of this vector, now we need to take this polynomial and split it using these elements. Okay? So let me write it like this. 2 minus 5t plus 2t squared equals. So I have a constant multiple times 1 plus t plus another constant multiple of 1 minus t, and then yet another multiple of t squared. So first of all, these are numbers, okay? So from here, I'm not going to get a second order term, which means that this has to be 2. Okay? So now let me put letters here, for instance. Let's say that temporarily this is A and this is B. Okay? So their sum is going to be 2. Right? And their difference is going to be minus 5. Okay. Remember I told you in the beginning of the class that you still have this conversion between systems of linear equations and matrix algebra. So I can safely turn this into a matrix operation. 2 minus 5. So the determinant of this is minus 1. Minus 1 is minus 2. So sending it to the other side, I have this. Minus 1, so this is minus 2. What was the rule? Flip these two. So minus 1, 1, and then put minuses in front here. 2 minus 5. These give you some numbers for A and B. Whatever numbers you have here, now you have that. Let me not finish this computation because I'm running out of time. The point is that now, with respect to this no basis, the same vector is going to look different. It's going to be, in the first entry, it's going to be A. In the second entry, it's going to be B. In the third entry, it's 2. Okay? Now on Friday, we're going to try to incorporate this different bases and turn arbitrary linear transformations between finite dimensional vector spaces into matrices. Okay? And that's it. Thank you. Okay, let's start. Good morning. So today we're going to keep working on this abstract setting, and finally things are going to sort of join together. Just to remind you, we're still wearing this straight jacket, and we have still matrix algebra. We can always still switch between systems of linear equations and matrix equations and do matrix algebra with it. And anything axiomatic we still have. What we don't have is being able to think as vectors in Rn, that is to say n tuples, as n by 1 matrices. We don't have that. And we don't have this correspondence between the space of, between linear transformations and matrices. So these two we don't have. Anything else we have.
What do you mean? Because, I mean, we've dealt with column vectors that are matrices already, right?
Yeah, but so when I write it like this, on the left-hand side, a typical element looks like this, okay? So when you take a vector here, you're taking something of this form. This is one form, and a typical element here is like this. So these two have different shapes, okay? Before, we were just using these as the same thing. I'm saying we're not using this. We're not using this, whatever this means and whatever this means, as identical things. They are, in a sense, identical. What I said was these are isomorphic vector spaces. But this isomorphism, so being able to think of this vector as this column matrix and vice versa, depends on the basis that you chose. And so just so that we emphasize this, just so that I emphasize this, I'm sort of separating, I'm splitting this, because otherwise it's not really making sense. It's like, why are we doing all this stuff? It's because switching from here to there depends on the basis that you're using for this space. Okay? I'm gonna remind it as well. Before delving further into this, I wanted to mention this. It's a very powerful statement, and this is why, essentially, why it's a very good idea. It's a very good heuristic to keep track of the dimensions of spaces that you're dealing with, in particular rank and nullity, for instance. And that is that for finite dimensional vector spaces, dimension, this number that you attach to the whole vector space, is the unique complete invariant. This means that two vector spaces are isomorphic, means that their dimension are the same, is the same, and vice versa. If you have two vector spaces and their dimensions end up being the same, then that means that they are isomorphic. Okay? So in terms of linear algebra, maybe as tokens they are different, but they are the same type. And what that type is completely determined by this one number, which is the dimension. Okay, I wanted to mention this. I'm not going to go into the proof of this because I don't think it is very illuminating at this stage, but if you feel like it, you might. So you have everything you need to verify this, assume that, and then get this and vice versa. So let me just leave it as an exercise. Okay, so let me recall what we were doing. We had this. So V be a finite dimensional vector space. So this means that it is a finite basis, right? And say beta, which is a tuple of vectors, beta 1 to beta n, is a basis. If this is the case, then we have this isomorphism of vector spaces. Then we have an isomorphism of vector spaces which I denoted by m sub beta. M sub beta takes as input a vector in this mysterious vector space, whatever it is, and gives you a translation of what that vector should be in terms of a column matrix. So okay. So how does it do it? Well, you take a vector in V. Since beta is a basis for V, I know that there are unique numbers, C1 to Cn, such that if I use those numbers as the coefficients for a certain linear combination, I get V. Such that B equals C1 beta 1 plus C2 beta 2 dot 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 Cn beta n. So once you have the splitting for your input, m sub beta of V is just going to be the column matrix whose entries are these specific numbers. Okay. So you see, this is really something like this. M sub beta of V is the matrix of V according to beta. Okay. So let me do an example. So what is the inverse of this? The inverse of it is that if you start with a matrix, C1 to Cn, well, take these numbers in this order, put them in to this linear combination. So C1 is going to be next to beta 1 and so on. Add them up, and that gives you a vector, and that's the inverse. Okay. So maybe I should write it like that. And similarly, m sub beta, it's a linear transformation. Recall that this was a notation for the inverse. This is merely C1 beta 1 plus C2 beta 2 plus Cn beta n. Okay, so m sub beta is giving you a sort of Rosetta Stone, if you want, that you can use to start with an abstract, this mysterious vector space, and interpret any vector in it as a column matrix, and vice versa. Of course, you should be able to go back. You can start with any column matrix and interpret it as a specific element in your vector space. It all depends on the basis that you choose, though. Okay. So here's an example. If I use the so-called standard basis, so 1, 0, 0, 0, 1, 0, 0, 0, 1. So I'm taking three three-dimensional vectors. This is a basis for R3. It's called the standard basis. Beta is the so-called standard basis, because this, in a sense, is the basis that we started with, even though we weren't mentioning that we were using this basis, then of course m sub beta of v1, v2, v3, right? I feed to it a vector, it's a triple of numbers, is exactly v1, v2, v3. Okay. Now here's one point. So for instance, in this case, m sub beta gives you an isomorphism from R3, it's one vector space, to the space of 3 by 1 matrices. And certainly this is three-dimensional, because to specify a column vector of size 3 by 1, you need three numbers. This has 3 dimensions. This too has 3 dimensions. And based on what I said over there, since these two vector spaces have the same dimension, they are surely isomorphic. That's not the point. The point is that this m sub beta is a very specific isomorphism. Okay? It's a very specific map. It's a very concrete map. You take a vector, gives you a unique output. Okay? That is determined in this way. Yes.
So the column v1, v2, v3, those are numbers?
Yes.
They're not vectors, they're numbers.
Yeah, they are numbers. Yes. Yeah, maybe I should write something like this. M sub beta of 2, 5, minus 1 is 2, 5, minus 1 written in this way. Okay, so on Wednesday I mentioned how we're going to be interested in different bases. So that corresponds to changing the coordinates, so to speak. And so just so that we can discuss this, let me give you this, what I like to call the universal diagram. Okay? So the universal diagram is for linear transformations. Okay? Linear transformations and matrices. So let's say that I have two vector spaces, finite dimensional. Two finite dimensional vector spaces. And let's choose bases for both of these. And let's say that V has dimension n, and W has dimension m. So let me choose two bases. So beta 1 to beta n is going to be a basis for V. And let's let gamma, this is also a tuple of vectors, this time vectors in W, be a basis for W. And let's let T to be a linear transformation from V to W. Finally, let T from V to W be a linear transformation. Now, my aim is this. Now that I have beta and gamma, which allow me to think of vectors in V as column vectors, as column matrices. And likewise, I can think of the vectors in W as column matrices. I would like to be able to think of this T, this transformation, too, as a matrix, okay, as a matrix multiplication. The aim is to be able to think of T as multiplying from the left by a matrix, as multiplication from the left by a matrix, using these charts m sub beta and m sub gamma. Using the linear charts or coordinates, if I want, m sub beta and m sub gamma. And here's how we can do this. So I'm basically going to draw a diagram, is what it's called, and it's sort of like a flow chart. I want to keep track of where is going what, or what is going where, I guess. So at the top, I'm going to draw an arrow from V to W, and I'm going to call it T. This represents this transformation that I'm trying to represent as a matrix. Okay, it's a linear transformation, but it is abstract. It's mysterious. I don't know what it is. Here, I'm going to have also vertical arrows that now will represent these linear charts. So this is going to be m sub beta, and this is going to be m sub gamma. Okay. And so just so that I keep track of what is an isomorphism and what isn't, I'm going to put this isomorphism symbol next to it as well. So this T doesn't need to be an isomorphism. Maybe it's not an invertible map, but certainly the charts are isomorphisms. So this isomorphism takes V and sends it to M of n by 1, comma R. Now this is something I know, okay? And this isomorphism m sub gamma is taking W and it sends it to M sub 1, M times 1, comma R. Okay? So I want a matrix, okay, in such a way that this thing is what is called commutes. That is to say, if I take a column matrix, apply my chart so that now I have this mysterious vector, apply my T to get a vector in W, and then use the new chart to get back another matrix with appropriate dimensions, now I want this whole thing to be equal to multiplying by some matrix. So this should be multiply from the left by the matrix, and I'm going to denote it like this. I'm going to call it M sub beta to gamma of T. Okay? So this means that it's the matrix of T where the inputs have basis beta and the outputs have basis gamma. Okay? And how do I figure this out? Well, all I need to do is to really read this chart. So in the book, they're using a slightly different symbol. I think in the book, the notation they use is this: T, and then an arrow like this from beta to gamma. I think this is the notation they use in the book. But it's the same thing. These two are the same things. Okay. So now let's do an example. Now, I stated it this way, but of course, you don't really need two distinct vector spaces or two distinct bases. You might as well use the same vector space and the same basis. And so let's look at this example, for instance. Let's look at P2. Recall that P2 was the three-dimensional vector space of polynomials of degree at most 2. So any vector in this vector space is of this form, right? And of course, what's the basis of this? We discussed this. Let's use a standard basis. So the standard basis in this case is, of course, 1 t and t squared. This is, again, the standard basis. And let's think of the transformation that has differentiation. So it's taking and I'm restricting differentiation to this specific space. Of course, I don't need to have my function to be a degree 2 polynomial to differentiate it. I can do much more, but we can certainly restrict differentiation to this space. Now, if you do this, what is differentiation? How does it work? If I were to feed to it this particular vector, the end result of this would be a1 plus 2 times a2. And this would vanish. A2t. Just so that it is more evocative, perhaps I should write it like so. Okay, let me use colors here. One t squared. And this really is a0 times 1. This is a1 times t, and this is a2 times t squared. On the one hand, the output is a1 times 1, a2 times t, and 0 times t squared. Okay, so far? So now let's try to apply this to this. So what is the matrix that represents differentiation in this setting? So I'm going to put everything into the universal diagram, and I'm going to try to read off that diagram, and that's going to tell me what that matrix should be. Now, in the diagram, the top row should be the unknown vector space. So that's P2. And instead of that T over there, I should be seeing D. Okay. Now, I only have one basis. So that means that I'm using both as beta and as gamma, the same basis. Okay. So this is going to be m sub beta. And this is going to be m sub beta also. And because these are isomorphisms, these are charts, global charts, I'm using the symbol to represent that. And as a consequence, maybe I should ask you, what is m sub beta of this vector? What is this? Exactly. So the end result is going to be a column vector or column matrix. Its first entry is going to be this, second entry is going to be this, third entry is going to be this. Not because I wrote these in this order, but because in my basis, this is the first guy, this is the second guy, and this is the third guy. Maybe just so that we're clear on that, let me write it like this. So A2 t squared plus A1 plus A0 plus A1 t. Okay. Now it wouldn't be A2, A0, A1. It would be A0, A1, A2 because the ordering comes from the beta, not by the way but not from the order in which I added these terms. Okay. So consequently, the output of m sub beta, this chart, is 3×1 matrices. So here I need this matrix. We still don't have it. But likewise, going from here to there, the end result is going to be a 3×1 matrix. So now I read the diagram. Okay? So we start from here. If I were to start with a typical vector, so A0 plus A1t plus A2t squared. Now, if I go down using this, now I have this vector A0, A1, A2. I can also go this way using the derivative. Using the derivative, now I have this new polynomial, a1 plus 2a2t, and let me just not write t squared. And now if I were to apply this coordinate chart, now I get another matrix. Okay, a1, 2a2, 0. Okay, now based on the universal chart, a universal diagram, my matrix that corresponds to differentiation with respect to these two bases, with respect to the beta basis, should be a matrix such that when I use it to multiply this from the left, I get this. So let's try that simpler. Let's just call it A. Thus, the matrix A is a matrix, is the matrix such that when I use it as a left multiplication for this, I get that. For any A0, A1, and A2, right? That's the point. This has to work for any vector whatsoever. Well, so now this is something we know, okay? So I erase it, but we're wearing the straitjacket, but still we know how to do matrix algebra, okay? And consequently, we know how to figure, so we still have the power to figure this out. So first of all, I know that this is 3 by 1. This too is 3 by 1, okay? And this number is the same thing as the number of rows of A, and this has to be the number of columns of A. So I know that A is a 3 by 3 matrix. And now I read off. Maybe just writing this over here is going to be easier to see. So I want 9 numbers such that when I put this matrix to the left of this matrix, I get back this new matrix. Okay? So this row times this gives me A1, which means that this has to be 0, 1, 0. Okay? And likewise, this row times this gives me this, which means that this has to be 2, these two have to be 0. And finally, this row times this gives me 0, which means this has to be 0. Okay? So there you go. This particular matrix corresponds to a differentiation. It supports everything that differentiation would do, insofar as you're looking at linear algebraic operations. Okay? So for instance, in this abstract context, of course we know how to how to polynomial multiply, and the derivative of the product is blah, 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 right? Like there's a rule. Now we don't have that anymore. It's gone. Because this encoding is not supporting that. It is supporting everything that you do in the context of linear algebra, though. That's the point. So you're losing some information, possibly, but you're retaining everything that is related to linear algebra. Okay?
This is just valid for polynomials.
Yes. Yes.
Would you do the same thing with like any differential equation, like where you could write a matrix for it?
Say again?
So like if I had like e to the x, then could I write a matrix that differentiates e to the x basically?
It depends on the basis you choose. Okay? So certainly, if you were to just consider all functions, it doesn't have a basis. Or it does in a sense, but we're not looking into that in this class. In this class, all we're doing really is about finite dimensions. What you can do is you can look at a two-dimensional slice using, let's say, 2 linearly independent functions, and that too would give you an expression like this. So for instance, one example is, consider this. Consider the space in the space of functions spanned by cosine and sine. Okay? Oh, I guess I can do this. Here's another example. Let me denote by of t, cosine of t, and g of t, sine of t. Okay, these two are functions, let's say, in this function space, and they are linearly independent. Thus, if I were to define as my mysterious vector space as their span, that would be a two-dimensional vector subspace of this, and f and g would constitute a basis for it. I'm defining the vector space V to be the span of f and g. Because they are linearly independent, that means that fg is a basis. So beta consisting of f comma g is a basis for V, and of course V is two-dimensional. It's a plane. Okay. So now let's do the same thing using this new basis, beta, in this new space. But my transformation is still going to be differentiation. Well, I'm again going to use the universal diagram. Okay, so this is m sub beta, and this is going into the space of 2 by 1 vectors, and this as well. And as I did over here, I need a matrix such that differentiation with respect to this basis is represented by multiplying from the left by this matrix that I discover. Okay? So now you see it's the same operator. The space is different, the basis is different. The matrix is going to be different also. In this case, of course, the representation will be a 2 by 2 matrix. Okay? It's not going to be 3 by 3 first of all. It's going to be 2 by 2 because I'm feeding to it a 2 by 1, and I want the end result to be 2 by 1 as well, which means that this representing matrix is going to be 2 by 2. It's the same transformation. Okay, it's differentiation. So, like I did over there, I'm just going to chase this diagram, is what this said. So, what is an element here? What is a typical element? Well, it's just a linear combination of f and g. So let's write it like this: AF plus BG. Now, with respect to this basis, this is stored in the column matrix AB. Right? Because the first element is F. So into the first entry, I'm putting the coefficient of F. The second element is G, the sine function. So I'm taking the coefficient of the sine function into the second coordinate. If I were to differentiate this, what happens? Well, if I differentiate F, that is to say, if I differentiate cosine of t, I get back minus sine of t, so minus g. And if I were to differentiate g, that is to say, if I were to differentiate sine, I would get cosine f. Okay. Now, again, I'm using the same chart to store this into a matrix. But you see now, the matrix is different. It's not this. First, I need to put B. And in the second entry, I need to put minus A. And I want a matrix that transforms this to this. And so it's going to be 2 by 2. And I'm going to reason as before. if I take this, multiply it by this, I want b, which means that this is 0, this is 1. Okay? And if I were to take this, multiply it by this, I want minus a, which means that this has to be minus 1, 0. So this now new 2 by 2 matrix is yet another representation. Okay? So you see, linear transformation is the same. It operates the same way. It doesn't matter. It could be mysterious, but it somehow operates the same. The reason why it is mysterious is because differentiation is coming from somewhere else. Right? It's not based on linear algebra. But if you want to think of differentiation in terms of linear algebra, now you have choices to make. And the way you encode a transformation as something that you know is going to depend on a bunch of different things. It's going to depend on the basis. It's going to depend on the vector space that you restrict your transformation to. Okay? Okay. Let me do another example. And this is related to an exercise I gave a couple of weeks ago in class. And this was about how the transpose operation, so taking the transpose of a matrix, is a linear transformation. Okay? So you see, what is the matrix of taking the transpose? It's not clear, but this procedure really allows you to actually answer that question. So here's an example. I'm going to denote by curly T the transformation from the space of 2 by 3 matrices. Okay, so now I'm pretending that this is the mysterious space. Because it's not really the space that is mysterious, it's this transformation that is mysterious. And I'm really trying to understand this in terms of matrix multiplication. So this, and it goes to M3 by 2. And all it does is it just takes the transpose. T of A is just going to be A to the T. And of course, A plus B to the T is the same thing as A to the T plus B to the T. And C times A to the T is the same thing as C times A to the T. In other words, this is indeed a linear transformation. Respects addition, respects scalar multiplication. That's all I need. And further, of course, if I were to start with a matrix here, take the transpose, that would be the inverse. Okay? So T is an isomorphism. In this case. So let's try to understand what its matrix is. So in order to answer this question, first I need to fix bases. Now what is a basis for a space of matrices? The standard basis for the space of matrices, for any space of matrices, is typically matrices such that only one entry is 1 and all other entries are 0. So standard bases for M2, 3, it's this, so I'm going to call it beta. Okay. Any 2 by 3 matrix is a linear combination of these, certainly. And certainly these are linearly independent. It's a basis. And for M3, 2, now I need to use 3 by 2 matrices. And just like I did in the case of 2 by 3, in the case of 3 by 2, again, I'm running through the entries. These certain span the vector space of 3 by 2 matrices, and they're also linearly independent. Okay? So now now that we have charts, I can come up with the matrix using the universal diagram. Okay. So this is my mysterious space. This is my transformation. It's also mysterious. This is my mysterious output space. Now I have my charts. For this, I have m sub beta going into, it's 6-dimensional, so going into 6 by 1. And this too is going into the same space. So now I want a matrix. So this matrix is taking a 6 by 1 matrix, multiplying it from the left, and giving you back another 6 by 1 matrix. Consequently, it's going to be a 6 by 6 matrix. The matrix that represents taking the transpose. So in this context, so in the context of matrix operations, if you're trying to sort of use linear algebra to simplify or, rethink operations with matrices, m sub beta, these global charts are also called like vectorization or flattening or reshaping. These are like also names that people use, especially in the context of computer science. And so A, B, C, D, E, F, according to this chart, goes to where? A, B, C, D, E, F. Now it's just a column. Applying the transpose gives you what? A, B, C, D, E, F. Now using the chart here, you see now we have AD, BE, CF. Okay. So the matrix that represents taking the transpose of a matrix should take any input like this, turn it into this. Of course, this is nothing but a permutation, which does make sense, right? Because you're just like reshuffling the entries. So A stays, B goes to, so 2 goes to 3, 3 goes to 5, D goes to 2, so 4 goes to 2. Maybe I should draw this as well. E goes to E over there, so 5 goes to 4, and 6 is it stays the same. So what is this? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1 and 6 are the same. 2 goes to 3. 3 goes to 5. 4 goes to 2. 5 goes to 3. Okay? And this also has a permutation matrix, of course, but let me not write it because I'm out of time. a permutation matrix. Okay. And that's all. Thank you. We have break, so it's going to be a 1 week break, and then when we come back, we're going to be discussing something a lot more concrete, signal processing. It's going to be another application of linear algebra. And the weekend, so the Friday of the week after the break, we're going to have our second midterm. Thank you. I'll have a nice break.